So 1.7 has us finishing out this chapter 1 stuff with this transition to algebra. And we defined what a term is in 1.6, and then we started off by talking about like terms. And if we wanted to add or subtract terms, they had to be like terms, right? That should be 2 words. Okay, so this is 1.6, the adding and subtracting, like terms. They have to be exactly the same in the variable component. Now, 1.7 is about multiplying and dividing terms. And so when we talk about these ones, we're not talking about like terms, we're talking about common bases. And really what common bases mean is that the exponent can be anything, but the letters have to be the same. So over here, like terms, everything had to be exactly the same in order to add or subtract them. Over here with 1.7, and what we're going to do right now is all about common bases. So we're looking for a cubed and a squared would be common bases. The common base is a, and it doesn't matter. They're not like terms, but they're common bases. So oftentimes when you're working through this, this separation here gets blurred, and you don't notice that the rules, well, people think the rules have changed, but they're not changing. They're just different rules for different operations. And so we're going to go back a little bit here and talk about exponential notation. So that was in our review chapter. And the reason that we did this is that we just wanted to recognize that it is a shortcut way for writing things all out. So if I have a times a times a times a times a, the more sensible way to write that is a to the 5. That's what this actually means. We've already seen these invisible things going on. And so I had said that if there's just a variable like x or y, and there's nothing, that is to the exponent 1, because that means y times nothing, or just y, right? So this was that invisible. And this one is just a little bit of a preview. We're going to talk about it more as we come up, as it comes up. But anything that is to the 0 is actually a 1. So don't worry about that just yet, but I'm planting that seed now for where that's going. Okay, so let's take a look at these ones. So we're finding the product of algebraic terms. So we're multiplying expressions with the same base or common basis here. So the base is the letter, or sometimes, and your textbook does this to us, a whole number. And it does that so you can kind of buy in and actually evaluate these things, because when they're A's and B's and X's, you can't really evaluate them. So this is the pattern. This is the model that the textbook says. So we have 2 terms here. And they have the common base x. Actually, it's technically 1 term, but we have 2 things here. I'm going to use the not precise word. And they have a as the letter. So the common base is a. And so in this, it's saying that we can add those exponents. So let's try one out. Let's expand it to test out that rule. So this one says we have a cubed and a to the 4th. So what this means, if we expand out a cubed, that's a times a times a. And I'm going to multiply this by a to the 4th. So I'd have 4 a's written across here. So even though this was the multiplication from the question, when I take a look at all of this, I get a to the 7th. And what I've done, I could, follow this pattern, right? This is to kind of expand it out and allow you to buy in. But a to the 3 plus 4 is a to the 7. And so that's the way, if I wanted to show my work without expanding it all out, this is that question shown with the rule being applied, right? With this pattern being applied. And so if you want, you can expand out all of these examples, but I think you go a little bit nutty and it takes up a lot of the page. I do think it's worth showing your work like I did on this one, where you're adding those 2 together. So off the top here, example A has the common base of A. And so that has my answer is going to be A, and I add those 2 exponents, 5 plus 7. So the final simplified answer, whoops, not to 17, 12. A to the 12. Okay. In B, we have this invisibility thing. And so we've got X with a 1 up there. You remember how I said it's not written, just like positives aren't written, but we know that it's there. So writing out my thinking for this, I've got an X, and the two exponents that I'm adding would be a 1 plus 8. So my final answer would be X to the 9. Here's one from your textbook, and every time I get to this example in my notes, I take a big sigh. I'm like, why do I keep doing this to myself? But let's try it two ways. So we're going to try the pattern here, and then we're going to evaluate it with our calculator with that y to the x button that we learned in chapter 0. So following the pattern, my common base is 3, and I'm adding the exponent. So I'd get 3 to the 6. If I take my calculator on that and evaluate it, I think I've got it written out in my notes here, I would get 700, I did this on a calculator, not out of my head, 729. So this is illustrating the point of what we're learning in the notes right now, but this is again to give you a little bit of buy-in, right? So try it this way. Do 3 squared, which is 9, times 3 to the 4th. And you can use that y to the x button on this, which is 81. And you should get the same value here. And again, with this one, it's an oddball because as we're learning algebra, this one isn't an algebra example, but it does give us a little bit of buy-in, hopefully, and remind us how to use our calculators because you get the same value whichever way you do it. So hopefully you're fully agreeing with me now. In this one, we have 3 y's here. So the common base is y. And in order to simplify this, I'm going to add the exponents. So I get as a final answer, y to the 10th. Not 10 y's, y to the 10th. Okay, for E, when I see this one, I've got x cubed and y to the 4th. Now, this is the first example that doesn't have common bases. These don't have common bases, so I can't do anything else. I could rewrite it if I wanted as x cubed y to the 4th because it means exactly the same thing, but I can't actually use this pattern that I've been learning in this part of the notes. Y to the 7 times y would be y to the 7 plus that invisible one, or y to the 8. Okay, so that was just the variable parts of it. We're going to move on a little bit here and talk about the what we do when they have coefficients in front of the variable parts. So basically all you do with this is multiply the coefficients and follow that exponent rule. So we'd have 2 times 3, so that's a 6, and it's x to the 3 plus 5. It might be worth showing your work. If you don't, that's totally fine, but it can save you some simple mistakes sometimes. Next one. And I'll throw the answers up for these last ones so you can check as you go. I'm not showing my work on them. Sometimes you really have to slow down. In this one, it's probably worth showing your work so that you don't make a simple mistake. They're not big numbers, but they are worth keeping track of carefully. The other thing to notice in K is that the last bit of it doesn't have an M, but we don't have to worry about that. Remember, we're in the world of common bases, not like terms when we're multiplying and dividing. Okay, so to round this out, we do have to finish the dividing part of it. And so similarly to the last page, we're going to talk about how we could see it expanded out, or we could see it, with the pattern. So this is the pattern, that's given. And what it says is that when we have common bases, we subtract the exponent. So let me try one that's a little bit shorter than this one because that's a lot. Let's try x cubed divided by x squared. So in this one, I could write out what it means, right? So I'd have 3 x's on the top and I'd have 2 x's on the bottom. Well, using the idea that anything divided by itself is 1, I'm going to cross out this x and this x, and this x and this x, and my final answer is just an x, or an x to the 1. So following the pattern, I'd have x cubed minus 2, or x to the 1. I get to the same answer either way, right? One way showing it all expanded out, and one way using the pattern or the exponent law that's outlined here. So hopefully you're okay with using the exponent law. If not, you can expand some of these out to give it a little bit more, to give yourself a little bit more buy-in. But in these ones, I'll show my work. So I have m to the 9 minus 6, or m cubed. Most of you are probably seeing the invisible ones here. So I have m to the 6 minus 1, or as an answer, simplified, m5. They do get more and more complicated. You can have more bases thrown in. Again, we're dealing with common bases. So I write it out, showing my work. Or you can skip that step, but I get a final answer of r squared s. I don't put the 1 up there. I mean, you can, but it's right without. Okay, D gets a little bit weirder. So we have a to the 2 minus 2 and b to the 4 minus 3. Now, a to the 0, if you remember, I said I was planting a seed and said it was 1. So you could go with me on that one. Or you can just think that something divided by itself is 1. And that's probably the simplest way to start thinking about a to the 0 as being 1. So that just goes away. And my final answer for this is just a B. You can stop me on that one if you want another example like that or clarification, but I'm going to move on. Okay, so the last one here, we have x cubed minus x squared, or sorry, 3 minus 2, because we have a 3 and a 2, I'm not using the right words. And then we have the y to the 5. Now, we don't have a y down below, so there's nothing wrong with just leaving that y to the 5 all alone up there. My final answer for this is going to be an x y to the 5. So I tried to throw in some oddballs here at the end just so that you have some experience. They can seem like trick questions, so doing your homework, definitely don't skip too many so that you don't deprive yourself of seeing one of those different type questions. So the last 4 on the page that round out this section of our notes have coefficients in them this time. And so really when we're dealing with the coefficients, we do the dividing, same as we did the multiplying with the coefficients before. In all of these, they are divisible evenly, and so that makes them easier. You could also think about them as fractions and reduce them as fractions. I think most people will avoid thinking about them as fractions, and so I won't expand on that in the notes just yet. So 4 divided by 2 is 2, and then the exponents following the pattern would be a 3 minus 1 as the exponent. So the final answer would be 2x squared. Next one here, 20 divided by 5 is a 4, and we've got an a to the 6, and we've got an a to the 1. So it's 6 minus 1 as my exponent for a final answer of 4a to the 5. Moving along, I'll put the answers up, but not maybe say them all out. All right, so oftentimes in these questions, it's fine when you do them like piece by piece by piece, but the challenge comes when we throw them all together. So we've got the last page here of putting them all together. In class, I'll give you some time to go through these. If you're just watching the video, then I'd encourage you to give them all a try because that mixed bag can make it really a challenge. When are you dealing with like terms and when are you dealing with common bases? And so check the key in Moodle if you're watching this video on your own or in class. We're going to do these 6 questions together. And that's the end of chapter 1.